ago, and we were discussing about the artificial neural network, where in the last couple of classes, whatever we said, whatever we discussed, was mainly called as the multi-layer perceptron. And we saw how, taking this good architecture that resembles the brain, we were able to solve some good problems. Any database that we gave, it would be able to have some kind of function with which it would be able to solve both the functional prediction problem as well as the classificative problem. But the neural network literature does not end with the multi-layer perceptrons. In fact, multi-layer perceptrons are extensively used in multiple domains, in multiple fields for multiple types of problems, but then there are other kinds of neural network models, and those are which we would be discussing today. So, out of all the various problems, apart from linear regression, if you may call it a neural network model, and the multi-layer perceptron, a few more that we are going to discuss. The first one that we will be discussing is called as a Radial Basis Function Networks. So again, these are neural networks, so there's a one network. What this means is that I'm gonna do some kind of tweak in the membership function. I'm going to do some kind of thing with the membership function, with the activation function. And by modification of activation function along with the little changes in the architecture, we will construct a highly customized model of the neural network. Again, on the lines of the multi-layer perceptron, again having a layered architecture of a couple of neurons. In a similar manner, we'll see how we can form these kinds of networks, and later on we might get into what are the properties of these networks, in what way do they differ from the multi-layer perceptron. So the first thing that comes up is what will be the architecture of these neural networks. That is what I will be dealing with first. So let me say that again it's the same problem. So the architecture will be some input layer neurons over here, some output layer neurons over here. Now the RDFNs, as they are called, they have just one single hidden layer. And of course, this is what is the architecture like. All these sorts of connections over here. And so on. So this is what is the architecture of the RDFNs. One input layer, one output layer, and exactly one hidden layer. Again, the input would be supplied at the input layer. There will be some kind of processing at the single output hidden layer over here, and there will be some kind of output over here. All these are weights from the hidden layer to the output layer. So let me call these weights as lambda 1, lambda 2, lambda 3, lambda 4, anything. There will be some weights from here to here. Now I do not have weights from the input layer to the first hidden layer, or from the input layer to the only hidden layer of these networks. In place, these hidden neurons have got some locations that are known as C1, C2, C3, C4, C5, C6 and C7 and so on. Let me say Cn. Any of these CIs is nothing but a vector of the form Ci1, Ci2 up till Cin, capital N, where N is the number of inputs that we had. And of course we'll see later why is it exactly this. So basically what happens is that in place of having weights from here to here, all I have is, I have a set of numbers over here, I have a set of vectors over here, with each vector comprising of a set of real value parameters. Now whenever I say I have applied an input I means that I have applied some input I1 over here, I2 over here, I3 over here, I capital N over here. That's what I basically mean. I have tried to apply some kind of input over here. What do I further mean is that my input vector I will be of the form I1, I2, I3 up till I capital N. So I is a vector. I is one of the vectors that I have applied over here. Now whenever I apply this input vector I over here, what basically happens is that each one of these neurons gets activated. Each one of these neurons gets activated, and I know how they will get activated. There is some kind of fusion where multiple input attributes will go together, and there is some kind of activation function that will work over it. So these two stages, 1 and 2, where the first information is collected by the neuron and secondly it passes over through some kind of nonlinear activation function, is, let me write it over here. This neuron, what it will do is that it will try to calculate the norm between C1 and the input vector I over here. So this will be I minus C1. This is what the first stage is, this is what the fusion is all about. And that's why both the vectors were given exactly the same size. That was the size of the input attributes N. This norm of course can be any norm, it can be Euclidean or the Manhattan or any purple norm that you may take. Normally preferred as the Euclidean norm. But it calculates the norm between the input and its location Ci. This will calculate the norm between I and C2. So any given general vector, any given general neuron of this place, what it simply does is that it tries to calculate the norm between the input and itself. That will be C1 1 minus I1 the whole square plus C1 2 I2 plus CI2 minus the whole square CIN minus IN the whole square, the whole under root. That will be what would the norm be if you take the Euclidean norm. So my first part is over, where the input was collected by the neuron. My second part is passing this input through a nonlinear activation function. Now it's a radial basis function network, so we take in a Gaussian activation function which is given by the equation fx equals to e raised to minus x squared. Which is given by this equation fx equals to e raised to minus x squared. So ultimately what happens if we consider an input I was applied over at this network, a neuron Ci, what it does is that it first calculates I minus Ci, the norm. Let me say this was the summation of this. Let me say this was the gathering of input by this neuron that was done. So let me take it was Yi. My output of any neuron I, what it would be equal to, it would be equal to Yi passed over the activation function, that means e raised to minus Yi square. This can be written as e raised to minus summation I minus Ci the whole square. This is what output comes up over here, over here, over here at multiple values of I. Now let me only consider one neuron over here. Let me consider one output neuron here. I will rub in these weights. Let me say lambda 1 was the weight from here to here. Lambda 2 was the weight from here to here. Lambda 3 was the weight from here to here. Lambda 4 was the weight from here to here, and so on. Let me say these weights were lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. In all, they would be, the last weight would be lambda n. In all, the last weight would be lambda n, where n is the total number of neurons over here, the total number of neurons in the hidden layer. So what happens is, I have got all the the individual hidden layer neurons over here, I get into my output layer. Let me say I am considering any output neuron OI. Now this OI having lambda 1I, lambda 2I, lambda 3I, lambda 4I as the weights. For simplicity, because I have already used I, let me use notation J for these terms. So my J output neuron of the output layer, it will have these kind of weights from the hidden layer. What happens is that this is just a simple summation. It is a submission of all OI, the output generated by the hidden layer neurons, whatever output they generated, weighted by these factors. So this is what my first part was, exactly as in the case of MLP. So this will simply be lambda Ji for all I 1 to n. For all I 1 to n, I'll get some kind of output. Now what happens in these function? And of course there might be a bias here, Bj, so I'll have to add a bias term over here. So what happens is that for any input, there is these neurons that get activated as per the Euclidean norm. They further get the information and a weighted addition of the output producer is done over here. Now the activation function of all these neurons is identity. So they don't have an activation function as such. So what happens is my final linear output becomes the final output OJ over here. Whatever output my system produces over here, at the time of weighted addition, it gets my final system output. So again we have tried to make it a system wherein we apply some kind of input, we get some kind of output as per this architecture. One thing to study would be that how is this activation function e raised to minus x square. The graph is given by this curve, and of course it's a normal Gaussian curve where x it increases and there is a steep dim fall earlier and it later becomes almost constant in nature. This is what this activation function is of any of the neuron of the hidden layer. Now again it can be seen that if my Euclidean norm of any neuron Ci, let me again take it at any general neuron Ci over here, if my Euclidean norm is very less, if the information that it has received after taking the Euclidean norm with its center over here, it's very less, the kind of activation produced will be very high. So neuron will get highly activated in such a case. When I say that the Euclidean norm between input I and the center Ci is very less, what I happen to mean is that there is approximately very little difference between the input I and Ci. So that means my Ci was more or less like my input. But on the other hand, if this Euclidean norm is very large, if this Euclidean norm is very large, what would happen is that my activation would be very large. So let me say that this was my information Yi. So this is the kind of activation that will produce. It will be very small. It will almost be tending to 0. And if I say my Yi is very large, I mean that I and Ci are very much distinct to each other. There is a very large difference between I and Ci, and therefore the Euclidean norm is large, and if the Euclidean norm is large, therefore the output produced is very large. So this is one of the ways that in which you can see this Radial Basis Function Network. Again, to state that since we have already made in some kind of framework, for any applied input I will get some output. So all I need to do is to find out idealistic values of these Ci's, these lambda i's, these bj's. All I have to find out the ideal values of all these parameters, the Ci's, the lambdas, the Cj's, the Bj's, and by using some kind of training algorithm, I can tune my system. I can always tune my system. I can find out the values such that whatever curve my output should have, whatever curve my output space should have, that is exactly the curve that is represented. I should know that whatever curve my database presents, so let me say this was the kind of curve, I can always tune these parameters so that this is the exact curve that I get based on all the machine learning algorithms. But what I do is that I don't restrict myself to this view. I give you an entirely new view of what the radial basis function networks are. This was when we considered them as a neural network. When we consider them as a set of neural network, we'll see another view of the RBFNs. Now suppose what I do is that I straight away plot the output space. So I will have some single output over here, multiple outputs divided up into single outputs, all with their own output space. So I'll get some kind of training data over here. My point is, if I can predict this kind of a function over here, this is what will be the output space for any input I1, I2 and so on. Let me parallelly draw one thing over here. I disregard the output. I only see what the input is. And I see where is it that the training data lies. So I draw my feature space over here. This is similar to taking this problem as a classificatory problem. This is exactly similar to taking this case as the classificatory problem, where all the outputs have been marked to S and whatever was the actual output of the system has not been considered. So it's exactly the same problem where I've just taken out where I've just up this dimensions of the output of space, where the output has been disregarded and whatever training data was found, that has been plotted up as classes. Into this what we call as the classificatory space or the feature space. Of course all classes are being marked as X because my output in real sense is continuous in nature. So I simultaneously draw these two kinds of plots. My aim is to get this plot. What I eventually say is that I cannot work with such large amount of training database. I probably cannot work with such kind of large amount of training database. I take up some points in this space. I take up some kind of points in this data, in this input space over here, all marked with CIs. For clarity, let me take it up like this. And of course, those represent some C1 over here, some C2 over here, some C3 over here, some C4 here over here, some C5 over here, in a multi-dimensional space. All with some outputs that is completely unknown, because I only have these points in this curve. The actual outputs to these points are all unknown. What I do next is that I try to give it some random outputs at all these points. I fix in some random outputs to them. So basically I'll get another kind of curve out over here. I'll get another kind of points over here where every input that I have randomly assumed has a random output. So it will be a very distinctive kind of, not a curve, but a set of points, regression over which you can formulate a curve. Now what happens is that I had this kind of database. Now let me consider any of the input over here. So let's say I consider any random input I over here. What again happens is that when I place an input I over here, different points over here, the different CIs over here, they calculate what is their distance to this point. So they all calculate these kinds of distances with their point. Now for some point of time, I assume that C1 knows what kind of output is found in this region. C1 is a neuron, C1 is a point that has some kind of idea what kind of outputs are found in this region. C2 has some idea that what kind of output is found in this region. C3 has some idea what kind of output is found in this region. C4 has some idea what kind of output is found in this region. So I say that C1 has, we know that out here at this region, outputs of the form of lambda 1 are found. Outputs of the magnitude of lambda 1 are found. Here we know that output of the magnitude of lambda 2 is found. Here we know output of the magnitude of lambda 3 is found. Here we know output of the magnitude of lambda 4 is found. Here we know output of the magnitude of lambda 5 is found as per this points that we plotted out over here. So any input general I over here in this space, and we are trying to find out what is the general kind of output that will be formed over here. What is that the general output that would be formed over here? What kind of magnitude do I present over here? What kind of magnitude do I expect anywhere around here? So again, let me say that because I is very close to C4, I can intuitively say that the kind of output that C4 has, I will have almost the same kind of output. Now remember that the regression curve out of these x that we plotted said in this point in this graph over here, we said it will always be a smooth curve. So if I is close to C4, it means that the curve will not make much transition between them. It will not make a very high amount of transition from one point to the other point. And therefore we say that I will almost have the same output, magnitude of output as C4. But then it's not exactly at C4, so there will be some amount of transition. We don't know what that transition would be. Again, I is more or less close to C3, so it will behave in similar way as C3 was behaving out over here. It will behave in some way as C1 is behaving out over here. It will not at all behave as C2 is behaving, but then C2 might have a general trend. If I know my output at some point that C1 is very high, my output at C2 is very low, so I know that most probably the output at I will be a bit lower. That is when, because of making a smooth transition, my curve will try to bend from reaching a very high value at C4 to a very low value at C2, and that's what I will have an intermediate value. Here let me say that these were the points. This was lambda 1, this was some lambda 2, this was some lambda 3, this was some lambda 4. If I have to point out output at any value here, I'll say it will almost be the value over here. It will have some trends of value over here. It may have some trends of value over here, and it may have very, very, very low trends over the value here. So what do I simply say? That my output at I is nothing but weighted addition over all these outputs. It's weighted addition over all these outputs. So simply I say my output OJ at any input I is nothing but my output at all these places that I have taken to be lambda J I, and of course the weight would be by some amount of function. If the weights distances are very small, then the weight would be high, if the distances are very high, the weight will be very small. So it is some function that takes in the distance as a measure. So let me say I minus Ci. And that's what exactly was the equation written back when I considered the actual neural network model. This is what's the activation function. This was what was the Euclidean norm, and this was what was the weights. And exactly thing you can see what I trying to do out somewhere over here. This is exactly what I am trying to do out over here. Based on all these lambda, I say that my output here is nothing but weightization of all these. Now one thing that I would eventually make out very soon is that lambda 4 over here has no contribution to input over here. It can be seen. Based on lambda 2 and lambda 3, if I say there's some distance into this lambda 3 and this distance into lambda 2, I'll get up mostly in this point. But I need not consider lambda 4 over here and I need not consider lambda 1 over here. So I need some mechanism by which I'll have to eliminate their entry into this equation. So I'll have to do some mechanism by which I'll have to eliminate this their entry into the equation, into this equation, because if I add it up right here, it will be this weight, this distance into this distance into lambda 4, lambda 2 into this distance and lambda 1 into this distance. I need some technique to eliminate these two. So what do? I use an activation function such that their contribution in deciding the output here will be almost 0. And when it's almost 0, I say that the contribution of these two are 0.6. Let me say the contribution of this is 0.6, this is 0.35. There are other neurons that make in 0.1 or let's say 0.199, and these have a contribution of 0.001 and 0.001. So 0.001 to me will not matter. It will try to have some kind of effect to it, which will eventually not affect the output over here. So in order to eliminate these, I pick up an activation function that reduces their weight to almost 0, and that is what I do by use of Gauss. If the distances is even a slightly higher, even the distance is slightly higher, the weight ultimately reduces to 0. And that's why only neurons lying close to it effectively make a contribution. Only lambda 2 and lambda 3 will make a contribution because their distance would be around here and around here. So they'll have a significant contribution, they'll have a significant contribution over here, but the others may not have. And of course there was a bias term that we did not mention up over here, that is something to do, that's just to lift in the entire curve up and down, that's another controllable parameter. So the neurons only work upon with the effective change, there is some kind of average that has been taken that will elevate the neural network out here. So again let me go up to the same two spaces, the input space and the classificatory space, or the output space, and this is what might now be called as the input space. What happens is that whenever I apply an input I, all these neurons, they calculate the Euclidean norms, and based on those Euclidean norms and they try to affect the output with kind of output that they possess. That's what eventually happens. So let me just try to draw only the centers over here, let's say C1, C2, C3, C4, C5, C6 and C7, and let me try to move along with the input I. So if the input I is here, this neuron will have maximum contribution, all of them the activation would be 0 because the distances are quite large enough, so the distance would be 0. What I do in order to better visualize this entire problem, I say that this is what is effective contribution. If a neuron gets excited to this degree, if a neuron is having this much amount of threshold weight, I'll say it's effective enough. Only for the purpose of discussion, I said to any threshold level. Let me say my Ci was effective till this level, my C5 is effective till this level, this is effective this level, and so on. After this, the effectiveness I'll assume to be almost 0. So now let me play around with an input I. When the input I is here, this has highest contribution, the contribution of everything is 0. As I go here, only C1 is contributing, only C1 is contributing, only C1 is contributing. If I go and enter over here, 5 has an effect. So it will be a mix of C1 and C5, others contribution 0. If I go further over here, C1 contribution reduces, it finally reduces to 0. If I go further anywhere over here, C2 gets intermingled up, all the other contribution are 0. So with this we come to a very interesting kind of scenario. If I introduce a term known as spread over here, again rewriting this equation into its normal form, Oj I equals to summation I equals to 1 to n lambda j e raised to a minus summation I minus ci the whole square, and I introduce a term sigma over here. Sigma will be denote the spread. If I just try to introduce the term spread over here, this distance, it means if I increase the spread over here, my Gaussian curve or my activation function will be something like this. That means if I make the same threshold level, the degree to which the neurons will be activated, let me say that the threshold level was the same, the distance to which the neurons will be activated, it will be even larger, and if I reduce the spread, the activation would be very large, will be very small. That is all I have done with the introduction of this term as the spread. So whenever I am trying, since I have introduced the term spread, the spread will effectively mean radius of all these curves. So I basically draw in 3 curves over here. Let me say one was this curve over here. There was C1, C2, C3, C4, C5, C6. The other curve was a C1 over here, a C2 over here, a C3 over here, a C4 over here, a C5 over here, and a C6 over here. And the other curve would be, let's say, C1, C2, C3 and C4 over here. What happens is that if I try to move around my input I over here, I know the output will be C1, other contribution 0. It will not change at all. It will not change at all. It will remain to be the contribution of C1 alone. It will remain to be contribution of C1 alone. Marginal contribution by C2, C3, C4, C5, C6. Because we know that threshold that we have fixed, it was fixed for an input that was almost 0. It wasn't exactly 0, so they will have some contribution. Here I do not know what is the output. Here it is undefined. So what I will eventually need to do is that if I need to find out these output at this place, I'll have to add some kind of CIs over here. So there will be some additional CIs over here that will cover up the entire space over here, that will cover up the entire space over here, and then I can probably try to find out some kind of output. So there are lots and lots and lots and lots and lots of CIs. Here of course there's C1, if I move slightly over here, C2 and gets activated, C4 gets activated, C4 doesn't get activated. If I move here, there are 3 neurons that get activated, and over here at any point of time some 3 to 4 neurons are giving effective contribution. Here all the neurons are giving effective contribution unless until I go towards the extreme. That is when I change this distance sigma, and as you can see the number of neurons was maximum here, it was minimum here, it was intermediate over here. Now we already know from that equation from the neural network architecture, any Ci is nothing but the neuron in the hidden layer. Any Ci is nothing but the neuron in the hidden layer. And the spread is nothing but the parameter of its activation function. Right now we assume that all the neurons have got the same spread, that spread is same, that is predefined in the problem. So basically, if the spread is less, you need lesser number of neurons to cover up the entire space. If the spread is very, I guess I've written down, okay. If the spread is less, then you need more number of neurons here. If the spread is more, then you need very less number of neurons to cover up the entire input space, because you know your ultimate goal is if you can cover up the entire input space by this set of neurons. What these are known, any CI, it may be known as a center, it may be known as a data center, it may be sometimes known as a data guide, and sometimes it is known as a neuron of the hidden layer. So whatever be the terminology used, but effectively this is a neuron. So what this entire thing is, it is the entire input space. And of course I am given some kind of X over here. I am given some kind of X over here in all these three spaces. And based on X, I can basically play around with my centers. I can try to move them all around. I can arrange the lambdas over here. If I consider the input space, of course the lambdas is not clear. It will come when I draw the output space. That will when it will be added up as a vertical axis, or the output space that will come up over here. So basically, if there are center C1, C2, C3, C4. Based on these X, all I'm supposed to do is to move them up in this space surface over here and calculate, move them vertically as lambda or as bias. So there's everything exciting that I can do. I can move around them once the spread is fixed. Once the spread is fixed, I can do all these kinds of things, moving them around laterally, amplifying them up vertically, and so on. And that is what is the role of a training algorithm. So the next issue that comes up in this, whether you take in the actual RBFN architecture, that was the first architecture drawn, exactly like the MLP, or you take up this architecture, the thing is if we can revise in a training algorithm similar to the backpropagation algorithm over there. Now, not to repeat that the problem is the same. The problem of training is the same. I am given a database and I have a set of parameters to train up to. I have a database and there is some kind of optimization that I need to do. So the similar backpropagation algorithm can be used. What I simply plot the error space. I simply take in all the parameters, that will be a CI over here, a BI over here, or might be a lambda I over here, and all the space of all CIs, BIs and lambda I's. CI will again be some CI1, CI2, CI3. If I plot this place, I draw this curve, then again based on some gradient descent approach, I can use a backpropagation algorithm. I can use any kind of statistical learning technique to tune in all the CIs, the biases or the lambdas, or I would say that the weights, the data centers and the biases. So I am not dealing with the training algorithm here. It's exactly similar to what we discussed in the MLPs. It is exactly the same training algorithm. What is of concern over here are two things. How do I change the spread? How do I fix the spread? And what ideally is the trade-off between a high spread and a low spread? So the important point is how do I fix in this spread, whether this is good, whether this is good, or whether this is good. Now, whenever I use kind of three things, then it must be clear that this is a case of normally an underfit, this is normally a case of overfit, and this is normally a case of an ideal fit. What basically happens is that okay, so even before we continue, whenever I say that there's underfit over here, overfit over here, and then intermediate fit over here. It's because of the additional neurons being caused. Because I added up additional neurons, they play an important role over here. So my discussion over here of these three would be exactly similar as was the case with the high number of neurons in the MLP. So what I see this problem, I see it as a problem of generalization versus localization. I say my neural network is localized if it gives an output only at looking at whatever was the kind of outputs in the near surroundings, at very, very near surroundings. This is what the case was here. It's trying to give an output that only when it was by consulting the outputs at the near surroundings. So let me say that I attack C1 over here. It has only one output. Training data based on which the CI must have been tuned, so it's only give output over here. Looking at the trends of output over here. Now what happens is that if there was a training data over here that was noisy. If there was a training data over here that was noisy, naturally this output is low. But because my network is trained to give an output over here, because my neural network is trained to give the correct output, the effect of this noise will be very large in the training of C1. So any output, any input in which C1 is dominant, any input to which the role of C1 is dominant, it will give all common outputs. It can never give you the correct output because of this noise over there. But then a noise over an X over here does not mean that C5 over here will give you wrong output. It does not mean C5 will give you wrong output. So my effect of noise is only restricted to this place. It's not restricted to this place. So if you look at the localized neural networks over here, that is when the number of data centers become very large over here, or in case of MLP, the number of neurons getting very large. The effect of noise is restricted only to a few inputs. But then that effect of points and those kinds of inputs is very bad. Your system completely gives you completely wrong answers, depending on what was the effect of noise over here. Again, like I say, it's kind of overfitting problem that these kinds of network have. It's exactly why the overfitting was happening in kind of in the MLPs when we increase the neurons. Increasing the neurons was making the shape very flexible, and the neural network could play a role more with the shape of the final curve to be predicted. And that's why it very adamantly placed up the data points. It very badly tried to fit in the curve, in which we saw that it was a very kind of bulky shape that the final curve assumed. Here also exactly the same thing happens. If I have a localized neural network in which the output is only consulted based on the kind of nearby outputs, if the output is only based on the nearby inputs, what ultimately happens is that the view of this neuron over here is restricted, it's highly restricted. It does not know what the global trends are. It does not know what the global trends are. So basically it gives you a very less training data. It needs to only train a small part of the input space. It needs to train a very small part of the input space, but all the global trends are all gone. So if this is my output space for any kind of input, what happens is that I can see that there is a general downfall in the value of output. But if I have restricted the view of my neural network to only this amount of space over here, let's say I had a training data over here, I had a training data over here, and I had another training data over here, that was exactly over here, my system will assume that the output at this place should be this because of this kind of training. My output will assume, and again let's say I have some training data over here, so these are training data. My system is trained only on this amount of data, so it will assume that the next point in that the input to any neuron here is this, to any neuron here is this. So it knows only the local trends that the curve was rising. It was only shown that the curve was rising. It does not know that there is a global trend over here that the curve was falling. And therefore all these outputs would be wrong until we get to this localized neural network that knows the global trends. But again, this notes the global trends, does not know the local trend over here. So again, because of the global trends being missing, there is a problem of overfitting that happens in localized neural networks. Conversely is the case with the generalized neural networks that have in a view of the entire input space out here. Exactly converse would be the case with the generalized neural network, where they got the entire space, where they got in everything that is up to them, but then it might be very difficult to train this kind of network. In MLP we said that the curve can take only a smooth shape, and the actual shape of the curve to predict it as per the number of neurons, it's complicated enough. It has got some 2 turns and my neural network is restricted to 1 turn only. Similar thing happens over here. So for any combination of CIs, the lambda i's and the BI's, for any combination of the centers, weights and biases, I am not able to get low error. The error is sufficiently high. That is because they are such large, they are so less neurons that I can play around with. There are only a handful of data centers that I can play around with. Only some of them that I can move about, I can scale about. All of them are large enough, so my workspace gets highly reduced. The kind of work that my workspace gets highly reduced. And then I'm asked to fit a curve, which is of course not possible always. So my generalized neural network, it has some global trends. It knows all the global trends, but it's very difficult to fit. The problem of noise is even different. If there is some kind of noise over here, it will affect all the neurons. But the effect will be very low because this noise will be captured by all the various training data sets over here. This data center was ideally being trained by only a couple of training data over here, but this neuron is being trained by most of the training data that it covers. So that was for generalization versus localization. I'll speak up might be a little about this because when you compare the MLPs to the RDFNs, if you compare the MLPs to the RDFNs, what you ultimately find out is that the RDFNs are more localized in their nature. In MLP, I had nothing that a neuron is being trained by only these neurons. Every neuron, every weight, be it from any layer to any layer, was being ultimately trained by all the data inputs. If I change it any weight, it affected everything. Change of even one single weight affected all the inputs and the outputs. So that's why my NLP is more of a generalized neural network. That's why sometimes it's difficult to control it out. My RDFN is a very localized kind of neural network. It said that the training time of the generalized neural network is lesser than that, is more than that of a localized neural network. Now effectively every neuron over my RDFN, it effectively gets trained by only a couple of inputs. It does not get trained by all the inputs. So every neuron has got a discrete set of inputs by which training happens. My NLP gets trained with all the entire training data set that is enforced upon the system. So that is the problem between generalized and localized. What again, the small curve that I would draw is that let me again draw the output space. Similar to the one that I had drawn in the previous case, where I mentioned things like there will be points like this. Let me say a point that says like this. Again, let me say there will be points like this. There will be points like this. There will be points like this. There will again be points like this. This is exactly what I drew up over there. Suppose my network is being trained by. Suppose a data center covers this. What will eventually happen is that it will predict the correct output over here. But suppose a data center gets this is what it will predict, and the actual curve is like this. This is when I have a very localized kind of neural network. It will predict all these wrong. Unless I come to this neural network, which is kind of trained by this. So ultimately I have the right trains being predicted by because of this problem. Conversely, let me say my data center was being given all these kinds of points. They were given all these training data points that I just drew. What a very generalized system would do, it will predict this. It will take this as a noise. It will try to take this as a noise, and it will form a true curve. So all these interesting facts are over, making the system too generalized, making it a very globalized view. If I increase the number of neurons in MLP, going more towards a localized side, of course it will be able to predict this ideal curve. So in MLP I need to increase the number of neurons to make that little more localized in nature so that it's able to predict this curve. But then when I say that I increase the number of points in MLP, what I eventually mean is that my training time automatically increases because of the numerous weights and biases that I've already added. For RBFN, I'll have to make the spread large enough so that both the global and the local trends are there. And then beautifully it gets this much amount of space to train itself with, and that is what covers both. Now all these centers that I draw were actually not this way, they were much more continuous in nature when it comes to the RBFN. So a best RBFN model is that has the maximum overlap between the various spreads, between the various neurons. It has the maximum overlap, the least number of neurons. Of course I'm moving towards the generalization side, so I'll have to state one point over here, provided the final error is low. All this exists, it exists fine, provided the final error is low enough. Now we dealt with a kind of learning that was based on statistical. We done with the supervised learning of the RDFNs. We've seen how using a supervised learning technique, be it a gradient descent approach, the propagation algorithm, sometimes statistical learning technique, the expectation maximization, and numerous approaches, all statistical in nature. I can do this. The good thing about the RBFNs is that I can take an unsupervised approach as well. What I ultimately do in an unsupervised approach is nothing but I have some training data that is available over here. I have some kind of training data that's available. I simply cluster these data. I apply any cluster and I decide say C1, C2, C3 and C4. So my centers in an unsupervised mode are available with me. I already got what my centers would be using an unsupervised learning. Now an unsupervised learning will never ask you what is the output. Clustering algorithm will never ask you what is the output. So using any clustering algorithm I can simply cluster these data centers that can effectively be the data centers that I get. Again you will have to decide upon the number of centers over here. The spread is of course always decided. Irrespective of the fact, any fact you have to decide the spread as a problem solving methodology depending on how much generality you need. I'll have to decide on these center, have to decide upon how many these centers have to be, and then I can form the entire Gaussian curve. And the lambda i's is again a simple technique. Lambda is very simple, so any input I know it will formulate to one of these data centers, and then if I know the output I can always return them out. If by chance towards the data center I can predict lambda i's, I can get done. So there's some kind of unsupervised technique that can be used. Many times what we do is that we try to find out these cluster centers, and that is what the training algorithm starts with. My training algorithm starts with all these cluster centers, and then it later tries to even more fine-tune these centers and try to control the lambdas and the VIs. So that's a kind of biased start to the gradient descent approach, where we starting with a really good condition that we know would many times be the ideal condition. So that's about the use of radial basis function networks. The key points that we had in our discussion, the key points regarding these regarding these networks that we had in our discussion was that they taken the Euclidean norm, they passed over the activation function as per the entire neural network architecture, so they behave exactly the same. But one more thing that we got is that we got a basic inspiration that they are a little more localized in nature when we compare to the MLPs. In the activation that any input, it activates only the nearby data sensor or the near neurons. We've got the basic motivation that whenever any input is applied, it will try to consult only the nearby data centers and try to compute its output and get the correct output. In any of the cases, the training algorithm is simply a statistical learning technique. It's a very, very simple statistical learning technique. And of course, towards the end, what we had a large amount of discussion was the problem of a neural network being more generalized to it being more localized. Now remember, when it gets very localized, it ultimately reduces to a lookup table. If I keep the state almost as 0, just ensuring the various neurons they touch each other, so this is nothing but simply a lookup table that I am mentioning, because I'll have to place all these neurons exactly where the training data is found. I'll have to place all these data centers exactly where the training data is found. So if I make in this kind of neural network, these are very good for machine learning. They have zero generality. These are like highly localized in nature and reduces the spread to almost 0 in nature. So ultimately they are reduced to a lookup table when it comes out here. More generalized, of course, network has the least problem with noise. It has the least problem with noise. The noise is kind of distributed in the entire network and the effect goes very, very low. Sometimes it's called as a problem of outliers. But then a very generalized neural network, you cannot generalize more than what the problem demands. So again we come to the discussion similar to what we had in the previous session, in the previous hour. How much the neuron should be, how much the spread should be. Again, you cannot decide upon yourself. You cannot decide upon yourself. The general methodology would remain the same. Keep the spread as large as possible, keep the neurons as less as possible. Try to see if the system error is less. Try to see if the system gives you error less enough. If yes, okay enough, proceed with it, and slightly increase the number of neurons and slightly reduce the spread. So again, when it comes to neural network, with the radial basis function network, the spread is a much important parameter. So you fix spread initially to a very large value, and as you go on, you keep on reducing till you get a decent error enough, till you get a decent error enough. And of course, you can always increase the number of neurons from a very low value to a very high value. If your number of neurons are very, very low at start, it will be an automatic consequence towards the later time where the spread will demand more neurons. So that was about the radial basis function network. The next model that comes up, especially for the classification problem, is the learning vector quantization. And the entire concept of learning vector quantization is what we will be dealing out in the next hour.